All right, folks, please welcome to the stage John Sutherland.
Good morning. So I don't have much in the way of small talk. My name's John. I have a website. But you're not here to hear me talk about myself, so you're here to hear about, hopefully, functional programming, which is what I'm going to talk to you about. So let's get started by sort of unpacking this title a little bit. So what is functional programming? This is a definition from Wikipedia. Mathematical functions, avoiding state and mutable data. The reason I'm a computer scientist or a programmer is because I'm scared of mathematicians. And this stuff about avoiding state and data, well, those are kind of our bread and butter, right? We have variables and we change stuff. That's what computers do. So given how awful this sounds, this is a humane introduction, hopefully, and I'll try to be as gentle as possible. Peter was also pretty strict with the 20 minutes, so we're going to go pretty quickly. There's a few things we're not going to talk about, and some of you may be pleased to hear we're not going to be talking about monads, which is fortunate for me because I don't know what they are. So why does functional programming matter? So we know that over time, systems grow in size and complexity, and the way that we manage complexity is with modularity. So what functional programming allows us to do is to compose complicated systems from fewer, smaller parts and simple data structures, which I quite like. So what does this offer us? So functional programming gives us a solid ground based on a few different things: higher-order functions, functional purity, and immutability. One of the important things about this, about learning what functional programming is it's a new angle to attack problems. So instead of just the same old object-oriented hammer, we can have our hammer and we can have our functional programming sickle. But some programs or some problems are still better suited to OO. So this is not always the best approach, but it's about using the right tool for the job. And I'm hoping to communicate a few different ideas with as little code as possible. So some of the examples are a bit silly. _JS is a small library that we use and contains a lot of useful functions for functional programming. And we'll be explaining those as we go as well. So it's probably enough chat. Let's get on with it. So higher order functions. So functions in JavaScript are first class, which means that they can be passed around the same way that strings or integers can. And so a higher order function is just a special function or a normal function in JavaScript where we can pass a function in or we return a value, a function as a value from that. So in this example here, and sorry these are not code highlighted, but so here makeAdder is a function which returns another function, line 2. The return function is actually also a closure, which means that when this function is called by map at line 7, it has access to the x variable. So closure it has access to anything which is in scope when it's created. And we all know this stuff already, hopefully. Map is also a higher order function because it takes the result from makeAdder 7 and it gets passed into map. So how does map work? So this is similar to underscore's implementation of map, where we basically iterate over a given list calling our passed in function func on each element in the list. I think the call to map in the previous slide is a lot more obvious. It explains what the intent was behind writing the code a lot better than a for loop. And we also avoid having these little I variables all over the place, which I think look quite ugly, actually. The second keystone of 3 that we're going to talk about is purity. So a pure function, an easy way to think about pure functions is they can be replaced with an object. So if the object would, the keys would be the arguments to the function, and the values would be the return values. And because pure functions always produce the same result, given the same arguments, they're exceptionally easy to test. So this function is impure because it accesses the x variable. So if someone here mucks around with the value of x somewhere else, this test will fail. Were this a pure function, we wouldn't have access to the x variable, and our test would always pass. Finally, immutability. So in functional programming, when we define a variable, we can't change its value. So in functional languages, I guess like Clojure or Haskell, things like that, almost all variables are immutable, which means we can't do things like append to a list or update objects. But there are ways around those sorts of things by creating new lists or new objects. And this sounds incredibly wasteful, but smart people work on this sort of stuff. So we don't really worry about it too much. So our implementation of map that we saw earlier has a couple of mutable objects, I and our result array there that we return. But map is a pure function because it only deals with stuff that's passed into it. And that's assuming nobody mucks around with the prototype for array and fucks up with the push function there, which, well, Ruby programmers might do that. But. So the inventor of Clojure, this guy Rich Hickey, much smarter person than I am, and you should maybe watch some of his videos because he maybe explains this stuff a lot better than I do. Asked this question in one of the pages on the Clojure website, I guess. If a pure function mutates some local data in order to produce an immutable return value, is that okay? Yeah, that's totally fine. That's his answer, not mine, by the way. Okay, so that's probably enough theory. So how might we actually use some of this stuff? So the Fibonacci, we've hopefully all seen this before, and I did warn you that the examples were quite contrived. But we want something we're familiar with so we can look at how this stuff works. Project Euler is just a set of simple problems that can be solved in clever ways. And they often build on previous problems. So I don't think number 2 builds on number 1, but some of the later ones do build on number 2. So the Fibonacci sequence, in case we're unfamiliar, the nth term in the Fibonacci sequence is the sum of the 2 previous values. So given the 2 starting values, 1 and 1, we add them together and we get 2. 2 and 3 give us 1 and 2 gives 3, 2 and 3 give us 5, 3 and 5 give us 8, 5 and 8 give us 13, and we can go on forever. So this is an implementation that we could use. It's quite an imperative one, lots of mutation going on. It gives us the correct answer, and it's quite short. And this would probably pass code review where you work and probably where I work. Apart from maybe those magic numbers, the 4000s and the 1s and the 2s and all that stuff. But I don't really like it. So our definition of the Fibonacci sequence is sort of split between line 2 and 9, where we specify the initial values and how to generate the next value. This only runs up to 4 million, and it only filters out odd values. This only really solves our specific problem. So how would we write this functionally? So we'd start with how to define the Fibonacci sequence. So this is really similar to our mathematical definition of the Fibonacci sequence. We can see at line 3 there that this looks almost exactly like the slide we had before. This function is pure, and I think it looks okay. So the next thing we need to do is we need to create a list or an array of these sorts of things. So this is how we might do it. We just generate this seq, and we keep calling fib on each value of I, and we return a sequence, and we get an array of Fibonacci numbers. There's a couple things wrong with this. This only calculates up to a maximum value, and if we actually run this code up to 4 million, or up to the terms less than 4 million, we end up calling our fib function 96 million times. So what we do for the first thing with the 4 million is we replace our max value with this predicate function, and we can pass in the Fibonacci, and also we can pass in the index. What this means is instead of going up to a maximum of 4 million, we could also say, give us the sum of the first 100 Fibonacci terms or the first 20. I also fixed the Fibonacci thing, and if you want to tweet about it and we can talk about it later, you can do that and then we can discuss it. But I'll show you what we do anyway at the end. So those predicate functions, here's a couple of examples. The first one here will generate the first 20 Fibonacci values, and the second one here will generate as a predicate function which will run up to a specified max or a given max value. So this is another higher order function that returns a function. So this is how we would use our max term function and our fib sequence function to generate the first 4 million Fibonacci numbers. And this looks quite simple because it's composed of the two smaller parts. So the next thing we need to do is we need to filter out odd values because we were only interested in the even values. So we define a function as even and we filter our sequence. So this is probably looks like cheating because we just have this filter, right? What does this even do? How does it work? So filter is very similar to our map implementation. With map, we call function and we add that to the result. With filter, if the return value of our predicate function is true, we add it to the result. If it's false, we just drop it on the floor. So we're almost there. We have all of our even Fibonacci numbers less than 4 million. We just need to sum them up. So summing a list, we could just use a for loop and we could just iterate over the list and add them all up. But the problem is we actually haven't covered reduce, which is the third sort of interesting functional programming thing that we haven't covered. So let's see how we might do that. So in other languages, Clojure comes to mind because I know it the best. We can the plus operator is just a function like anything else. But in JavaScript, it isn't. So we need to create this add function, which given two values, will just add them together. And then our sum then is just to reduce. We reduce the list using the add function with an initial value of 0. So this is a little bit. It's not complicated, but it's not obvious at first sight how reduce works. So what reduce does is it takes the initial value 0, and here we see it in green, and it calls add with the initial value and the first element in the list, 1, which gives us the result 1. It then calls add again with the return value from the first call and the second element from the list to give us 3, and then again and again and again until we get our result 15 at the end there. What's interesting about reduce is that it can actually be used to implement both map and filter as well. So we have all the parts now. We have our Fibonacci numbers. We are able to sum a sequence of numbers. So let's see how it all fits together. And this is it. So what's interesting about this, to me at least, and hopefully to you, that we generate our Fibonacci numbers, we filter out the odd values when we sum them. What's interesting is this is very similar to how we pipe command line programs together in the shell. So if you think about our Fibonacci sequence, it could be one function that just generates Fibonacci numbers. Then our filter is like a grep, and finally our sum is BC or DC, whatever it's called, which would add up all of our numbers for us. So let's take care of the last few bits and pieces that I mentioned. So our fib function, we mentioned that this got called 96 million times. It's actually 96,631,126 times. And also remember that pure functions, which this is, can be replaced with table lookups. Now I'm not going to write out a huge object of all the Fibonacci values, but one thing we can do is we have this what's called memoize. So memoize, what it does is it basically caches the return values for every time we call a given function. So as long as our function is pure, which in this case it is, we can use memwise. So instead of 96 million calls, we now have 34, which is much better. And this is one of the things that functional programming gives us, which is there's lots of these little things that we can do. We can, things like memwise, map, reduce, these things are really nice things we can add together to produce quite complicated, complex systems. So what have we done? Well, we've seen map, filter, and reduce, which are the sort of cornerstones of functional programming. We've seen how purity makes testing easier, how composing higher order functions to create complicated systems increases reusability, hopefully. But there's still one improvement I would make, and this is to our Fibonacci sequence function, which was the longest function we defined. I would replace this with a lazy sequence. So one thing we can do, this is ECMAScript 6. We use this function star, which declares a generator function, or the generator of a generator function, and the yield keyword. So if we, the way this is used is we would call fibs, and we keep calling next, and we keep generating increasing values from the Fibonacci sequence. We can talk about this in the other room if anyone's interested afterwards. So if you're interested in this, Jim's talk from 2 years ago is a really fun talk. He builds up this Y Combinator, which helps us deal with recursion in functional programming. It's really, really good talk. Phil's talk from last year and Phil's talk from 20 minutes ago, both also good talks to watch. You've already seen one of them. And Michael Focus's book, Functional JavaScript, is quite good. It goes into a lot more into underscore and things like that. There's a few blog posts that we can talk about. If you're interested in how we can use functional programming for interfaces, Facebook's React.js is the thing to look out for. And I asked Rory, the guy that organizes Edinburgh.js, if I could talk next month about more stuff like this. So if you're interested in that, you should come along to that too. Which just leaves me to thank my colleagues at FanDuel who are hiring. They helped me with feedback and my proposal and whatnot. And thank you to everyone involved with the conference and to you all for voting and for listening to me babble on for 17 minutes 42 seconds.